Today, as you know, the topic is countability. Now let's start countability. So, okay. So this is the chapter for today, infinity and countability. Now, before we move on in this chapter, okay, let me just tell you one thing that uh, like if you have, let's assume there are two boxes. Okay, so this is your box 1 and this is box 2. In this box 1, let's assume you have red balls. So in this box 1, basically you have many red balls you have, and in this box 2, let's assume you have blue balls. Okay, so there are blue balls in this box. Now the question is, let's assume there are, you can see here there are four red balls in this box 1 and there are six blue balls in this box 2. Okay, now if I ask you which box has more number of balls, then you can say that okay, box 2 has more number of balls, because you can count, you know counting. So that's why you can say that okay, answer is because this box 2 has 6 balls and this box 1 has 4 balls. So you can directly say that this box 2 has more number of balls than this box 1. Okay, so this is a very because you know counting, you are a very knowledgeable person, so you know counting, so that's why you can do. But think about the scenario when you did not know counting. Like let's assume you were child, very little child you were. Okay, or maybe some illiterate person who does not know how to count. Okay, or maybe before this counting was invented. Okay, like okay, many years ago, before this counting, this 1 2 3, this counting was invented. So before that, how people used to count? Okay, so what they would do, so actually this counting, how to count, this counting started from here. The very basic thing, you can say, the very basic thing is, you can say what you will do, you will take one red ball. You basically you will take one red ball you will take, and from here, from this box 1 you will take one red ball, and from this box 2 you will take one blue ball, and you will put them away. So basically you removed one red ball and you removed one blue ball. Then what you would do again, you will remove one red ball again also. So basically one red ball you will remove and one blue ball you will remove. Okay, so like this you will do. Actually this is what is counting. Okay, so you can see again what you will do, because you don't know counting, you don't know what is 6, you don't know what is 5, you don't know counting. Okay, you don't know these numbers. Okay, now if I ask you which box has more number of balls, then what you will do, a illiterate person will do like this. Okay, so one item from here, one item from here, he will cross check. Then one item from here, one item from here, he will cross. Then again you will remove one item from here, one item from here. Again you will remove one item from here, one item from here. Now at the end, when this box 1 is empty, at that time you can see this box 2 is not empty. This is not empty. Okay, box 1 is empty, box 2 is not empty. So you can say that box 2 has more number of balls than box 1. So this is how actually this counting started. So this is the basic principle, this is the basic idea of counting. This is the you can say, from here, from these type of things, this counting actually started. So you can see that this complete chapter, this chapter that we are going to see, this countability, this complete chapter is based on these basic principles, you can see. So actually let me tell you one thing, that a illiterate person, okay, who does not know what is this 6 5, okay, these things, or you can say a child who does not know these numbers, they they know countability better than us. Okay, so you will be surprised, because actually this very simple principle, what we are doing, in this simple principle what we are doing, we are basically putting these elements, okay, elements from this set and elements from this set, we are putting them in one to one correspondence. We are taking one item from here, one item from here, then one item from here, one item from here. So we are putting them in one to one correspondence. For every red ball we have a blue ball, every red ball we have a blue ball. So like this, and this is the basic principle of, you can say, this is the you can say foundation of counting. From here counting started. Okay, and this simple principle if you know, then you already know countability. Okay, so now after this, let's see. So actually if we want to go in formal definitions, so far we have seen this very informal example, but if we want to go in formal definitions of countability, uncountability, all these things, then you must know some, you can say, some some prerequisites. What are the prerequisites? So like this, what is a function, what is a one-to-one function, okay, and what is on-to function, bijection. So these things are prerequisite, okay, function, bijection, and one-to-one function, okay. So actually I am not going to teach all these things because these are very basic things, and since we are in the last 1 month of gate exam, so it does not make any sense if we are still studying these basic things, okay. So I assume that everybody knows these things: what is a function, what is a bijection, what is one-to-one function, what is a surjective function, basically what is a on-to function. So this is my assumption that you already know these very basic things. Now, okay, this bijection is very important that we will use. What is this bijection? This bijection is also called, the another name for this bijection is basically one-to-one correspondence. One-to-one correspondence that we have already seen. Just now what we saw, that was actually one-to-one correspondence. So the another name for bijection is one-to-one correspondence. In this, what you do, you have a set and another set. So set A, set B. In this set A you have some elements, in this set B you have some elements. So bijection says that, or one-to-one correspondence says that, for every element here, for every element here you have unique element here. Also for every element here you have unique element here. Basically for every element of set A you have unique element of set B, and for every element of set B you have unique element in set A. So this type of situation, this is called one-to-one correspondence. You are putting elements of set A and elements of set B in one-to-one correspondence. Basically one item from set A, one item from set B, and you are basically putting them like this. So this is called bijection, okay. Such type of function which puts element of A and element of B in one-to-one correspondence, such type of function is called bijection, okay. So these basic things I already assume that you already know, okay. These are very simple things. Now, so now before we move forward, so you can see, just for the sake of completeness, okay, I have put these details like what is a function, what is one-to-one function, what is a on-to function. Just for the sake of completeness, I will share these slides uh, with you, okay. You can join our Telegram group. The link for the Telegram group will be provided in the comments. You can say in the description we will provide the link, and in that Telegram group I will share these slides. So in these slides basically I have put all the information that is needed, okay. Just for the sake of completeness, every information is present here, okay. Like this slide, basically in this slide you have what is the definition of function and all these things. One-to-one function you already know. Basically for different elements you have different mapping. So this is the definition of one-to-one. If you have different elements like 1 2, these are different elements, so they must map to different element. Like 1 is mapping to A, 2 is mapping to B. So this is one-to-one function. On to function means basically this set B, this set B must be covered. Like for every element of set B you must have at least one pre-image. So you can see this set B must be covered. So this is the definition of on-to function. You already know all these basic things, okay. Now the next chapter, that is our what is cardinality. If I ask anyone what is the definition of cardinality, then actually many people actually they will give me this definition, that if you have a set, let's assume I have a set, and if I ask you what is the cardinality of this set S, then many students will say that the number of elements in S. Actually this definition is somewhat correct but not exactly. For example, if I give you a set, okay, in this set, if I ask you what is the cardinality of this set, then you can say that cardinality of set S is basically 3. Okay, cardinality of any set is denoted by like this. If you have a set S, then this is how you denote cardinality of set S. So you can see if you have this set, then definitely you can say cardinality of S is 3. But remember, if you have set of natural number 1, 2, 3 and so on, if you have set of natural number, and then I ask you what is the cardinality of natural number, now you will say that okay, cardinality of natural number is infinite. Now my next question would be set of real number. Consider the set of real numbers. If you consider the set of real numbers from minus infinity to infinity, then if I ask you again what is the cardinality of set of real number, then you will again say that set of real number are also infinite. Now the question is, now the main confusion is that this is also infinite, this is also infinite, can we say that set of natural number is equal to basically the cardinality of set of natural number is equal to the cardinality of set of real number? This is the question, because this is also infinite, this is also infinite. So now the main question is, can we say that cardinality of set of natural number is equal to cardinality of real number? Can we say, is it true or not? If it is true, then you can see one thing. If it is true, then you can see one thing, that many many students will say that this set of every natural number is real number, but there are real numbers which are not natural number. Okay, so you can see, if this is real, if this is true, then also there is a like we should consider these points. Okay, like every natural number is real number and so on. So but if this is not equal, let's assume this is not equal, then we need to decide which infinity is greater. We need to decide whether this infinity is bigger than this infinity. Now if you put this question in front of a school child, let's assume a ninth class student, if you put this statement in front of him, that this infinity is greater than this infinity, then he will be confused, or maybe he can call you dumb. Okay, but actually you are not dumb, because there are many different levels of infinity, or you can say there are different categories of infinity, and this is all that we need to study here. Okay, basically different infinities can also, you can say, be different. So that is the point. Okay, so everything we will discuss, don't worry. Now first, before we go to infinite sets, let's just talk about finite set, and let's get away. Okay, let's take it, out of our way. So for finite set, everything is very intuitive. Everything is intuitive. Okay, because for finite set, what you can see, if I give you a set, let's assume I give you a set a comma b comma c, and if I give you a set b where 1 comma 2 comma 3 comma 4, now you can definitely, now what you can say, you can definitely say that this set b is this set b has the cardinality greater than cardinality of set a. You can definitely say this just by looking at this set, because the set b has 4 elements and set a has 3 elements. So cardinality of set b is greater than cardinality of set a, because you can count, you can very easily count. Okay, so that's why this finite set, when we are dealing with finite set, then these are very intuitive. Okay, so anyway, okay, there is nothing interesting about this finite set, so that's why I just wanted to take them away from our way. Now we will actually, mainly our focus will be on infinite set. But here one thing you can see, okay, here one thing you can see, let's assume you do not know counting. Let's assume you do not know what is 3, what is 4, you do not know. Okay, you are an illiterate person. In that case, if I ask you which set is greater, which set is bigger, set A or set B, which set is bigger, if I ask you this question, then what you will do, you will basically put them in one-to-one correspondence. You will remove A from here, 1 from here. You will remove one element from here, one element from here. You will remove one element from here, one element from here. Now at the end, now this set A is empty and this set B has one element. So at this point you can say that set B has more cardinality than set A. So at this point you can definitely say. So you can see this was the example that we were looking at, but you can see in the finite set also this bijection, this one-to-one correspondence method works. You can see. Okay, so when we put them in one-to-one correspondence, you can see we cannot put them because this B has more number of elements than this A. So that's why you can see this finite set also obey the principle of one-to-one correspondence. Okay, but these are not interesting because these are very intuitive. You can count and you can just solve any question. Okay, in the gate exam they are not going to ask you what is the cardinality, whether the cardinality of a finite set is equal to the cardinality of another finite set, because you can very easily, you can count them and you can just solve it. But the interesting chapter that we need, the interesting area that we need to focus is infinite set. Okay, now, when you are dealing with infinite, when you are dealing with infinity, remember, actually not about this computer science, not about this discrete mathematics, not about this countability, but whenever you are dealing with infinity, in any field of mathematics, in any field of science, okay, then you should take care. Okay, so like I will give you one example where this infinity is not that much intuitive. Okay, so let's see one example, and this is called Hilbert's Grand Hotel. Okay, so this is basically called Hilbert's Grand Hotel. Why I am giving you this example? Because I just want to tell you that what you think of infinity, you should change your thinking little bit, because this infinity, when you are dealing with infinity, then many things are not intuitive. Okay, many things are not intuitive, so that's why we are looking at this Hilbert's Grand Hotel. But okay, before we look at this Hilbert's Grand Hotel, let me give you some motivation why we should see this Hilbert's Grand Hotel. Let me give you some motivation. The motivation is like this. Now consider there is a hotel, okay, and in this hotel, so there is a hotel, and in this hotel, let's assume there are three rooms, okay, so there are three rooms in this hotel. Now, if there are only three rooms in this hotel, and let's assume every room is occupied, okay, and now you go to this hotel and you want a room, but every room is occupied. You can see in this hotel there are finite number of rooms, only three rooms are there, and now you want a room but every room is occupied, so you will be denied. The hotel manager will tell you that okay, we don't have any vacant room, so you can go. Okay, you can see. So this is the case when you have finite number of, when you have finite when you are dealing with finite set. You can see here we are dealing with finite number of rooms because the number of rooms is finite. So this is the scenario, very intuitive scenario. Okay, of course, if every room is filled, if every room is occupied, then how can you accommodate any other person, any new person, of course. So this is very intuitive. But now what is this Hilbert's Grand Hotel? This Hilbert's Grand Hotel has infinite number of rooms. So this is a hotel. Okay. In this hotel, basically, you have infinite number of rooms. There are infinite number of rooms. And because there are infinite number of rooms, and let's assume every room is occupied. Every single room, every room is occupied. Remember, every room is occupied. Now, if every room is occupied in this hotel, then a very, you can say, anyone can say that if every room is occupied and a new person comes and this person, let's assume this is me, I want a hotel in this room, then definitely this hotel manager will tell me go. I don't have this is the intuitive notion. Okay, this hotel manager will tell me that okay, go, I don't have any vacant room, every room is occupied. Then what I will say, I will say this: you have infinite number of rooms. Let's do one thing. Shift this person to in this room. Shift this person in this room. Basically, shift this person in this room, this person in this room, this person, and so on. Basically, shift every person in the next room. Every person will be shifted in the next room like this. If you do like this, if you shift every person in the next room, then because there are infinite number of rooms, you can do this. You can shift every person in the next room, then automatically this first room will be empty, and hence I can say that I can accommodate this. So you can see one thing, even though this Hilbert's Grand Hotel, this is an infinite number of rooms, there are infinite number of rooms, you can see that even though these all these rooms were occupied, all these rooms were occupied, but still I can I can give him this room. Okay, I can you can say give this new person I can allocate one room. So this is why you can see that when you are dealing with infinity, then things are not intuitive. Okay, like in this scenario, when every room is filled, every room is occupied, but still we can put a new person. Okay, and in this scenario, when the number of rooms were finite, in this scenario I cannot accommodate a new person if every room is filled, if every room is occupied. So hence this example will tell you, this Hilbert's Grand Hotel, this example will tell you that when you are dealing with infinity, then you need to take care. You cannot deal with infinity the way you deal with finite set. Okay, now another example, another so why I told you all these things, because let's assume that you have two set. Okay, assume you have, instead of shifting, we could have given same room by saying that okay, there are infinite number of rooms are there, take infinite plus first room. So 9, you have infinite number of rooms, but you are not constructing a new room. Okay, basically there are infinite number of rooms, and we are saying that, okay, just shift every person in the next room. Okay, so like that, we are not constructing a new room. Okay, but anyway, I think you got the idea that when we are dealing with infinity, then things are not that much intuitive, that much straightforward. Okay, so things become tricky basically. Now the next point is, let's assume that you have let's handle the finite set. Let's assume you have a set A, and this is like this, A B C, and you have a set B, and let's assume this is A B C D. Now if I ask you which set has more cardinality, then very easily you can say that this set B has more cardinality, and the reason that you will give is this, that every element of A is already present in B. You can see every element of A is already present in B, but this B has extra element. Basically you will say that B is a superset of A. B is a proper superset of A, so definitely the cardinality of B is greater than cardinality of A. Yes, this is true, but this is true only in the finite set. When you are dealing with finite set, at that time this logic is true, that if cardinality of B is, if B is superset, B is proper superset of A, then cardinality of B is strictly greater than cardinality of A. This is true. This is true, but only for finite set, when you are dealing with finite set. But when you are dealing with infinite set, then these things are not true. Let's assume you are dealing with infinite set of natural number 1 2 3 and so on, set of natural number, and set of even natural number. Okay, like 2 4 6 8 and so on. Now if I ask you which set has more cardinality, whether this set N or this set E. Okay, so now there might be many other opinions, different opinions can be there. First opinion first opinion will be that, first opinion can be like this, that set of natural number is infinite, and set of this even natural number is infinite, and infinite basically is equal to infinite. This is the first opinion, very simple opinion. Okay, now the second opinion will be, they will say that, see, every element of this set E is already present in this set N. You can see every element of set E is already present inside this set N, but we have some extra elements like this 1 3 5. So some extra elements we have in set N, so definitely the cardinality of set N should be greater than the cardinality of set E. So this is the second opinion. It makes more sense, of course. It makes sense to many people. Many people will give you this argument. Okay, so but actually this argument is also incorrect. Why? Because when you are dealing with infinite set, then things are not that much straightforward as you think. Because now I will show you, I will prove it to you, that set of natural number has the same cardinality as set of even natural number. I will prove it to you. So you can see this first opinion and second opinion, both these opinion are incorrect. And the correct opinion, what is the correct opinion? That is basically your, just become illiterate. Okay, you are very knowledgeable person, you have taken computer science, okay, you have done BTech, but just become illiterate. What a illiterate person will do? So basically, how to do counting? What is the basic counting? Basic counting says that you have set of natural number, and this is your set of natural number 1 2 3 4 and so on, and this is set of set of even natural number 2 4 6 8 and so on. Now what I will do, I will put them in one-to-one correspondence. I will put them. For example, I will put this 1 with 2. Okay, I will put this 2 with 4, this 3 with 6, this 4 with 8, this 5 with 10, this 6 with 12, and so on, like this. You can see one thing, that every number here, if I have number x here, if I have any number x here, let's assume x, then I am mapping this x to 2x. Okay, now you can see one thing, you can just notice one thing, that what I have done, I have put set of natural number in one-to-one correspondence with set of even natural number. You can see for every natural number you have unique even natural number, because if you have a natural number x, then you have a unique natural number, a unique even natural number 2x. And also for every even natural number, if you have any even natural number, then for that you have unique natural number y. So you can see that what I have done, I have put set of natural number and set of even natural number in one-to-one correspondence. In one-to-one correspondence, basically it's like this. I will remove this from here, this from here, remove this from here, this from here, this from here, this from here. So like this, you can see that because I have put them in one-to-one correspondence, for every element here I have element here, and for every element here I have element here. So I can say that set of natural number has the same cardinality set of even natural number. So this is the proof, very simple proof you can see. Okay, now you can see this is the proof, and this is the principle of counting. Whatever we have seen, this is the principle of counting. Okay, or you can say this is the this is how actually we should count when we were child, when we did not know any count, any numbers 1 2 3. At that time, if someone tells us let's assume subtract 7 minus 4. Okay, let's assume you have 7 oranges, let's assume you have 7 oranges and minus 4 apples. Then what you would do, you would do like this. You would for one orange you will remove one apple and so on. Okay, and then finally seven sorry, 3 oranges will remain. So this is the basic principle of counting that we have seen, many examples we have seen. So by this time, after Hilbert's Grand Hotel and many other examples that we have seen, at this point of time, I think you are convinced that you can see when we are dealing with infinite set, then we should not apply those logics that we apply for finite set. Remember, every logic that you apply for infinite set is also applicable for finite set. So if you have a logic that is applicable for infinite set, okay, like the definitions that we will see for infinite sets, okay, those definitions are also applicable for finite sets. But the intuition, the logic, the definitions that we have for finite set, those are not applicable for infinite sets. So okay, so that's why we need a definition, we need a you can say we need some procedure, or you can say definition, to define cardinality. And the cardinality is defined very simply. The very simple definition of cardinality: if you have any set A, any set B, it can be any set, remember, finite, infinite, okay, any set. It can be also any set. If you have two set such that you can put them in one-to-one correspondence, two set such that you can put them in one-to-one correspondence, you can put them in one-to-one correspondence, then what you will say, you will say that cardinality of set A is cardinality of set B. This is the definition of cardinality. This is how scientists, mathematicians, everyone has defined cardinality. Remember, this is the definition. It does not need any proof. Why? Because this is how we have defined cardinality. We need some notation, we need some procedure to compare the cardinality of a set with another set. Okay, and we have seen that the notation, the definition that we have for finite set is not applicable to infinite set. So that's why mathematicians have come up with this definition of cardinality. And this definition is applicable on finite set also, infinite set also, countable set also, uncountable set also. You can have any set and this definition is applicable. So this is the definition. You have set A, set B. Then if you can put them in one-to-one correspondence, then we will say that they have same cardinality. And if they have same cardinality, then you can put them in one-to-one correspondence. This is the definition of cardinality. And now, for example, after this definition, you can very easily see that this set, okay, a very simple example, if I take this set and if I take this set 1 2 3, then these two sets are having in equal cardinality. Why? Because I can put them in one-to-one correspondence. You can see, since I can put them in one-to-one correspondence, so I can say that cardinality of A is cardinality of B. This is simple because here we are dealing with finite set. And I told you, I have given you example where set of natural number has the same cardinality as set of even natural number. This example also I have given you. Okay, here you can see we were putting set of natural numbers in the one-to-one correspondence with set of even natural numbers. So all these things that we have seen, now let's move on. Okay, so the definition of cardinality, this is the point, and the definition is like this. Okay, so two set A and B have the same cardinality, means we will say basically that cardinality of A is equal to cardinality of B. When we will say this, if and only if there is a bijection. Bijection means one-to-one correspondence. There is a bijection from set A to set B. And bijection means basically we are putting element of set A and element of set B in one-to-one correspondence. Okay. So this is how we have defined, this is how mathematicians and everyone has defined, you can say, cardinality. Okay. So now let's see the next point. So yeah, so this definition we have already seen that this definition is also applicable on finite set. Okay, so that we have already seen. Now let's see the next point, finite versus infinite. Okay, so this example we have already seen. You can always get a room at Hilbert's Infinite Grand Hotel. This is the statement. Okay, this is a nice statement. You can see this tells us that what is the difference between finite and infinite. When you are dealing with finite and when you are dealing with infinite, then what is the basic difference? And this is the difference. This one example will tell you everything, because you can always get a room at Hilbert's Infinite Grand Hotel, even if all the rooms are occupied, even if every room is occupied, then also you can get a room at this hotel. All you have to do, just shift every person in the next room, and then you can definitely do this. Okay, now let's see. So this is Hilbert's Grand Hotel, and this is the basic idea that we have seen. Okay, you can see, just shift every person in the next room, and then you can accommodate the new guest. The new guest will go in the first room. This is how you can do. And remember, after you do this first room, after this new guest has been accommodated, now if another person comes, he also can be accommodated. Okay, you can also allocate him also room. What you will do, again you will shift every person in the next room. So you can see, this is the point, that in this hotel you can always get a room. Okay, so this is this is why dealing with finite set and infinite set is this tricky, you can say. So the definition you need to remember, and this is the definition of cardinality. From today onwards, if anyone asks you what is the definition of cardinality, then do not say number of elements. No, do not say that. Okay, because that definition is only applicable for finite set. Hence, this is the definition that you should use. Two set A and B have same cardinality if there is one-to-one correspondence between A and B, then we will say that they have the same cardinality. And if they have the same cardinality, then we will write that cardinality of A is equal to cardinality of B. Now we have another definition. This definition is also intuitive. What is this definition? Let's see. And this is actually, this is a theorem by you can say, okay, I can't pronounce this name, but you can read this name. Okay, this is a theorem by this person, and this is a very useful theorem. What he says that if you have a set A and you have another set B, remember they can be finite, infinite, we don't care. They can be any set, any set. And let's assume that you have a one-to-one function. One-to-one function means injective function. If you have an injective function, if there exists an injective function from set A to set B, there is an injective, not bijective, injective function means, okay, some elements can be some elements need not be covered. Okay, these elements need not be covered. Basically the point is that from this set A, if you have injective function into this set B, then we will say that cardinality of A is less than or equal to cardinality of B. Okay, this is quite intuitive actually, but the okay, so the okay, I will tell you why. Okay, this is actually intuitive, but the proof is very hard. Okay, so this is the theorem and it has been proven, but the proof is very hard, and of course beyond gate level. Maybe if you research in this area, then maybe you can go through the proof. But you can see, but this is a very intuitive result. If you have a set A, set B, any set they can be, if there exists an injective function, this is an injective function, remember, then we can say that cardinality of set A is less than or equal to cardinality of set B. Now assume that you have two set. Assume you have a set A, set B, and you have a injective function. Remember, injective means basically your one-to-one function. You have a one-to-one function from a to b. Also, okay, remember, this means if you have an injective function from a to b, this means cardinality of a is less than equal to cardinality of b. And also, let's assume that you have injective function, another injective function, okay, may not be same. You can have another different injective function, maybe some different injective function g from b to a. So this means cardinality of b is less than equal to cardinality of a. So what I'm saying that you have two set a and b such that we have injective function from a to b. Also we have injective function from b to a. Then this will mean that cardinality of a is less than equal to cardinality of b, and this will mean that cardinality of b is less than equal to cardinality of a. And these two things, they will mean that cardinality of a is equal to cardinality of b. Okay, so this is the theorem that has been proposed by this person. Okay, you can just read his name. So this theorem, okay, let me just tell you. Remember, this is a theorem. This is not a definition. What is the difference between definition and theorem? Definition, when you see that something is definition, then basically it means that this is how people have defined it, so you don't have to prove it. This is how people have defined it. But when you see a theorem, then theorem means you can prove it. So theorem can be proven from the definitions. Okay, anyway, okay, don't go into it, but my point is that this theorem is very useful. Okay, so now if from now onwards, let's assume you need to prove whether two set have the same cardinality or not, then you don't have to find a bijection, because you already know the definition of cardinality. If I give you two set a and b and I ask you whether, let's assume they have the same cardinality, but you need to show me a bijection between them. Okay, a one-to-one correspondence between a and b. Then sometimes finding this bijective function is hard. Okay, it is sometimes it is very hard to find this bijective function. Okay, but what you can do instead, you can simply find injective function from a to b, and you can find injective function from b to a. Like this you can do. This is much easier. Basically, finding bijective function between a and b, this is many times this is very hard. Instead, what you can do, you can just find injective function from a to b, and you can find another injective function from b to a. If you can do this and this, then you can directly say that cardinality of a is equal to cardinality of b. Let me give you one example to to prove, like, to show what I am saying. So assume that take any example. For example, set of natural number. You know what is set of natural number? 1, 2, 3 and so on. This is set of natural number. Also take n square. What is n square? That you already know. This is Cartesian product, basically n cross n, Cartesian product of two set. So in this you have ordered pairs. First element is coming from set natural number and second element is coming from set of natural number. So like this, for example, 0, 0 can be there, 0, 1 can be there, 1, 0 can be there, 1, 2 can be there, and so on. So set of ordered pairs you have, and basically in these ordered pairs, first element is coming from n and second element is coming from n. Now you have set of natural number and you have n square. Now the question is, can we say that set of natural number has the same cardinality as set of this n square? The question is, can we say that n has the same cardinality as n square? This is the question. Okay, so now the one definition that we have seen, the first definition of this equivalent, okay, this equivalence we have seen this, and in that definition we want to find a bijection. In that definition we want to find a bijective function between n and n square. But what you can do instead of finding bijective function, what you can do, you can find an injective function from n to n square. Also you can find injective function from n square to n. So you can do them separately. If you can do this and this, then definitely you can say that they have same cardinality. Okay, so now let me give you a injective function from n to n square. injective function from n to n square. This is very easy, because in my injective function what I will do, consider this function. In this n, what I have, I have 1 2 3 4 and so on. What I will do, I will give you injective function like this. I will map this 1 to whom, in this n square, to whom I will map, I will map it to 0 comma 1. Yes, I will map this 2 to 0 comma 2. I will map this 3 to 0 comma 3. I will map this 4 to 0 comma 4 and so on. You can see this is an injective function from set of natural number to set of n square. Very simple injective function I have given you. You can see different elements have different images, you can see. Okay, so this is very easy to give injective function from n to n square. So now we have injective function from n to n square. Now let me give you injective function from n square to n. Injective function from n square to n. And what is the idea? Idea is like this. In n square, what you have, for example, you have 0 comma 0, you have 0 comma 1, all these things you have. Okay, for example 1 comma 2 and so on. These are the things you have in n square. In n you have 1 2, sorry, okay, 0 1 2. Okay, before actually, let me tell you one thing. Now some students might be confused in set of natural number from where 0 is coming. Some students might be confused here, so let me clear that point first. In set of natural number, whether to put 0 or not, that is conventional. Means what it means? It means that in computer science, mostly actually all the computer science authors, I have seen most of the computer science authors, they think that 0 is a natural number. So what they will do, they will put this 0 in the set of natural number. But the mathematicians, okay, the mathematical you can say authors, they do not consider 0 in natural number. So whether 0 belongs to a natural number or not, that is a conventional thing. Okay, so you don't have to worry about it. Okay, if you want to take it, you can take it, or if you want to leave it, you can leave it. That is your wish. In gate exam, those professors who set the gate exam questions, they know this thing. Well, okay, so they will give you, if it is, let's assume, if it is affecting your answer, whether to take 0 in natural number or not, if this is affecting your answer, then definitely they will give you whether 0 belongs to set of natural number or not. So don't worry about this. Okay, okay. So this is a conventional thing, different authors define differently. Okay, anyway, we are assuming that in this example we are assuming that set of natural number has 0. But okay, that is not required. If you do not want to take 0, then just remove all these things. Like if you don't want to take 0, let's assume you don't want to take 0, let's assume, then you can remove them. You can start from 1 2 3 and so on. Okay, this one element won't change anything. Okay, now anyway, now you can see that what I will do, I need to give you a injective function from n square to n. So what I will do, I will map this 1 comma 2. What I will do, if I have a pair m comma n, then that pair I will map to 2 power m 3 power n. Why I am doing this, from where this is coming? Let me tell you why I am doing this. Because this is basically prime factorization of some number. For example, if I have 1 comma 2, then to which number I will map it? I will map it to 2 power 1 3 power 2. You can see this is a prime factorization of 18. So basically what I am doing, I am putting this 1 comma 2 in 18. I am mapping this 1 comma 2 to 18. Are you getting this point? If I have a pair m comma n, then I will map this pair to 2 power m 3 power n. Okay, this is a prime factorization. 2 power m 3 power n 5 and so on. These things are prime factorization, and prime factorization of a number is unique. You already know this thing. If you have a number, any number, then its prime factorization is unique, you can see. So that is the reason I am using this prime factorization, because if I have any number, then the prime factorization is unique. For this 1 comma 2, this will map to 18. No other element can map to 18. For example, this 1 comma 1, to which element it will map? It will map to 6, because 1 1, this will map to 2 power 1 3 power 1, basically 6. So you can see one thing, that every element of n square, what I am doing, every element of n square is mapping to unique element. Remember, this is just like, okay, some students might be thinking from where this from where I am getting this is coming from experience, okay, and you don't have to worry about from where it is coming. I am just showing you that this is how you can make injective function, okay. My idea is not that, like in gate exam they are not going to ask you to show this injection. They are not going to ask you this. In gate exam they are going to ask you whether n has the same cardinality as n square or not. This is their question, and I am just showing you all the definitions that we have seen so far. I am just giving you example for those definitions. So you can see this is how you can map this is how you can find an injective function from n square to n. Very simple injective function you can find. If you have any pair m comma n, then you need to map it to 2 power m, 3 power n. And this is a prime factorization, and prime factorization of any number is unique. So that is why this is an injective function. And now we have injective function from n square to n. So from n square to n we have injective function, and we already have injective function from n to n square. So we can say that cardinality of n is equal to cardinality of n square. So this is another way of showing equal cardinality. Just another way. You don't have to show bijection, okay? Because let me tell you one thing. By showing bijection many times is very hard. So that is why this rule, okay, this rule is very helpful. Anyway, okay, let's move on. So now let's, so far we have not, so far I have not used the term countable, uncountable. These terms I have not used so far, you have seen, okay. Now I will use. So far we have only discussed what is the definition of cardinality. This is what we have discussed so far. You just need to understand this definition, nothing else. This is the most important thing. So we have seen the definition of cardinality, and we have also seen the definition of like when two set are equal, they have same cardinality or not. When two set have same, if you have set A, set B, then when will they have the same cardinality, or when they will have different cardinality, that we have seen. Same cardinality means there is, you can say, one-to-one correspondence. If there is no one-to-one correspondence, then you can say they have different cardinality. So this definition of cardinality we have seen. Now actually these natural numbers, set of natural numbers, these are very you can say interesting, or you can say these are very important. So what we have done, these mathematicians, what they have done, they have given a special name to those set which have same cardinality as set of natural number. They have given a special name to those set. So basically if you have a set, let's assume you have a set S, such that set S has same cardinality as set of natural number. If this is the situation, then we have given a very special name to this set S. And what is that set? What we will call it? We will call it countable. So this is the word, you can see. Countable is just a word that we use for those set which have the same cardinality as set of natural number. Now here actually one thing let me tell you, so that there is no confusion. Different authors define this word countable differently. Okay, so there are some authors, what they will do, they will do like this. They will say that finite is, okay, different, and countable is different, and uncountable is different. So they will do like this. This is their classification. Okay, they will say that finite is different, basically finite is not countable and countable is not finite. So this is their classification. So some authors define like this. Okay, now there are other authors you can say. Other authors, what they do like this. They define countable and uncountable, just two things, either countable or uncountable. And in this countable they say that either countably finite, or you can say countably infinite. So whichever you have studied, either you have studied these authors or you have studied from these authors, both are correct, okay, there is no difference. And you don't have to worry which to follow in the gate exam, because the gate exam question maker knows all these things. Okay, the gate exam professors, they know these things. Even in one institute, let me tell you, in ISC, I have taken two different, you can say, from two different professors. I have studied their notes, and one professor defines like this, and another professor defines like this. So in the same institute, you can see there are different professors who use different conventions. So you don't have to worry about these conventions. Okay, the gate exam question maker, those professors, they are very knowledgeable, and they will take care of all these things. But my suggestion would be, actually I follow this thing. So let's follow, in our complete lecture we will follow this. What we will say, we will say that we have countable and uncountable. Whatever is not countable, that is uncountable. If something is not countable, then that is uncountable. Okay, and in this countable we will have either finite set or countably infinite set. So basically every finite set is countable. Okay, like this. So this is what we will use. Now in the previous definition, now let me change it. So the definition of countability, now I will define what is countable. Let me define it again. Countable set. If you have a set S, then this S is countable. This S is countable if and only if, this S is countable if and only if S can be put in one-to-one correspondence. S can be put in one-to-one correspondence with some subset of some subset of n. So this is very simple definition. What I'm saying that a set S is countable if and only if S can be put in one-to-one correspondence with some subset of n. Like this, for example, if you have considered this set as ABC, you can see that this set is countable. Why this set is countable? Because I can put this set in one-to-one correspondence with subset of some subset of n. What subset I will take? Let me take this subset. So you can see with this subset of n, I have put this set in one-to-one correspondence. So I can say this set S is countable. So this is the definition we can use. Okay, this is a very simple definition. In this definition, basically, we have covered the case of finite set. Because of this subset, we have covered the case of finite set. Okay, basically we have said, in this definition we have said that every finite set is also countable. That is the point. So this is the definition that we will use. This is the definition that some authors use. Okay, now these finite set are not interesting, as you already know. So we will focus on infinite set. Now assume you have an infinite set. Of course every finite set is countable, that is okay, but assume that you have an infinite set. Now for that infinite set we need to find whether that is countable or uncountable. That is the interesting area, whether that is countable or uncountable. Okay, that is what we need to find. And for this we have two methods to find out this. Given an infinite set, this is the given infinite set, whether this is countable or uncountable, this is what we need to find. And for this we have two methods, actually three methods we have. First method, method 1, what you do, let's assume you have infinite set S. Let's assume this set S is there. So the first method is, what you do, if you can show a bijection S, and there is a bijection, let's assume some bijection, if you can show with set of natural number, if you can show me a bijection from set S to set N, then we can say basically one-to-one correspondence. If you can put them in one-to-one correspondence, then we can say that S is countable. In that case we can say S is countable. Either you can do this, and for this method we have taken one example where we have shown that set of natural number has the same cardinality as set of even natural number. This method we have already basically one example we have taken for this method. Second method, method 2. Method 2, I told you what you do, you show injective function from set S to N. Also you show injective function from set N to S. What you do, from S to N you you give injective function. Also what you do, from set n to s you give injective function. If you can do both these things, injective function, injective, if you can do both these things, then you can say that set of this s is countable, s is countable. Okay, and the method 3 that we will use, this is the method 3 that we will use. So this is the method, this is the most, you can say, simple method, and this method I will use, and from now onwards I will tell you what is this method, and you also need to apply this method in any question, and you will be able to solve each and every question. So this method, just wait for this method. Okay, this is a very, you can say, simple and nice method. This will solve all the question, every single question you can solve using this method. Okay, so we will discuss this method. Let's see what is this method. Let's see. So before we look at this method, you can see these notes. You can see integers are very important, basically set of natural numbers or integers, all these things, these are very special. So we give a special name, and what is that special name? Basically, if you have an infinite set, then that set will be called countably infinite if there is bijection from n to a. Okay, so now this you already know. So we will look at the method 3, but before that let me summarize few points. Point is like this: if there is any set S such that this set is countably infinite, let's assume this set is countably, what is the meaning of countably infinite? Countably infinite, S is countably infinite means set S has the same cardinality as set of natural number. So this is the meaning of countably infinite. This is the definition of countably infinite actually. Okay, so this definition we have already seen. And remember, and what is the definition of this equivalence? Set of the cardinality of set of S is equal to cardinality of set N. This is the definition that you already know, either method 1, method 2 or method 3. Now let me tell you what is the method 3 that I am talking about. The method 3 is called countability lemma. Countability lemma. And this countability lemma actually I found in a research paper. I was going through this research paper, and in that I found this countability lemma. So many students, if you have already studied countability from somewhere, from any coaching or from any author or any, so most probably you have not studied this countability lemma. Sir, why are we taking natural number to prove countable uncountable? Because Komal, that is how we have defined it. That is how we have defined it. I told you. See here, you can see this is from a university. These slides, all these notes actually I have taken from different articles. So you can see here, this is how we have defined it, the countable. Because actually what we need to, we need to see whether different set have the different cardinality or not. I told you that there are different levels of infinity. We will come back to it. Okay, but there are actually different levels of infinity. The lowest level is, if you see the lowest level of infinity, that is your set of natural number. That is your basically countable. This countable is basically the lowest level of infinity. Okay, means every infinite set that we have here means every countable infinite set. Okay, like set of natural number, set of integers, set of even natural number, set of rational number, these things, these are the lowest level of infinity. After that we have higher levels of infinity. Okay, remember there are different levels of infinity. It's not just two levels, no, there are many different levels of infinity. For example, these are countable and all these are called uncountable. But remember, in this uncountable also we have different levels of infinity. I will show you, I will prove this, that I will prove that there is always a different level of infinity. This I will prove at the end. There is always a different level of infinity. Even your real numbers are here, your real numbers are here. So even there are you can say sets, there are set which have more cardinality than set of real numbers. Anyway, all these things we will see. all these things are coming. But this is how we have defined countability. Countable set means which has the same cardinality as set of natural number. Now this countability lemma is very very important. Okay, and let's try to understand this countability lemma. First of all, this countability lemma, where we will use it. So if everyone, if there is anyone who is sleeping right now, if there is anyone, then you just wake up now, because this is the most important part of this lecture. Okay, now in this you will see that in the gate exam, if you have seen, many questions are like this. They will give you some set will be given set S, and they will ask you whether S is countable or not. This is what they will ask you, whether S is countable or uncountable. This is they will ask you. You can see many, all the questions are like this. So to do this, what you can do, you can just apply our countability lemma. This says that what you do, this is your set S and this is your set of natural number. Let me start it 1 2 3. Okay, this is your set of natural number 1 2 3 4 and so on. So you don't have to put bijection, you don't have to put injection, nothing. Okay, you don't have to show bijection, you don't have to show one-to-one correspondence, you don't have to show injection from S to N, N to S. All these things you don't have to show. Okay, don't do all these things. What you do, just do like this. For every element of S, for every element of S, you should have unique number here. Means, for example, maybe A is, for A you have 3. Means for every element of S, you must have unique number in set of natural number. And remember, for every element of set of natural number, you must have a finite number of elements. Finite number of elements. Not unique element. I am saying finite number of elements. Every element, for every element, you must have finite number of elements. Okay, so if you can do like this, then we will say that S is countable. Okay, this will be clear with the example. It will be clear what I am saying. Let's take some different examples, and we will also solve all the previous year gate questions. First example, let me take a very simple set, a finite set. Let me tell you, let me take A equal to A B C. Now what I will do, this is A, this is B, this is C, and this is my set of natural number 1 2 3 4 and so on. Countability lemma says that now I want to check whether this set A is countable or not. This is what I want to check. So what I told you that all you need to do is like this. For every number here, you must have unique number here, and for every natural number here, you must have finite number of elements. So what you do, very easy, just put this one. Okay, just cover everything. Like basically what I am doing, to this one I am assigning these finite number of elements. You can see these are finite number of elements. So I am putting these elements, all these elements, A comma B comma C, all these elements I am putting with 1. Now I told you one thing, that every element here must have unique element. You can see A is going to 1, B is going to 1, C is going to 1. Okay, every element is going to unique element, and here this element 1, this number 1 is going to finite number of elements. You can see these are finite number of elements also. But remember, these two also must go to finite number of elements, so it can go to empty set. Empty set is finite set, so this also can go to empty. Basically all other natural numbers, they can go to empty set. You can do like this. So because I can do this, hence I can say that this set A is countable set. Did you get it? The definition is very simple. This definition of countability lemma, to prove whether a given set is countable or not, very simple. All you need to do, you don't have to go for bijection, you don't have to go for injection, bijection, all these things, one-to-one correspondence, all these things you don't have to do. All you have to do, just put, for every element of set A, you must have unique natural number, and for every natural number, you must have finite number of elements. Okay, if you can do this, then we can say this set A is countable. So this set A is countable. Let's take more example. For example, consider this set of integers and set of natural numbers. So sorry, set of integers, whether set of integers is countable or not. So let's prove it using countability lemma. Very easy to prove. This is your set of integers. Basically here I am putting what I need to prove. I need to check whether Z is countable or not, and here I have set of natural number. What I will do, you know, This is how I will do. I will put, if you have, for example, if you have 0 and then you have minus 1 1, then you have 2 minus 2 3 minus 3, what I will do, I will do like this. I will put these, for example, 2 comma minus 2, I will put them to 2, 3 comma minus 3, I will put them to 3, 4 comma minus 4, I will put them to 4, okay, and so on. 5 comma minus 5, I will put them to 5, and so on. This is how I will do. Okay, and these three remaining elements, minus 1 0 and 1, these I will put to 1. So what I did, you can see countability lemma says that what I have done, for every element you can see I have a unique element. For 0 there is a unique element, minus 1 unique element, 1 unique element, 2 unique element. For every element here I have a unique natural number. Also for every natural number I have finite number of elements. Finite number of elements is important. With this one I have finite number of elements, with this two I have finite number of elements, with this three finite number of elements. How many elements, that does not matter, but finite number of elements. With this four, finite number of elements. So because I can do this, hence I can say set of integers that is countable. So very easy, you can see this definition is very easy. It will make your all the questions will become very easy. Now let's show that set of rational number is countable. Set of rational numbers, set of all rational numbers is countable. Again, all you need to do, just apply this principle that I have told you. Just apply this countability lemma. What are rational numbers? For example, you know all these are rational numbers, like negative p by q. Set of rational number means what can be written like this: a by b, where b is not equal to 0. A and b are integers. This is the definition of rational number. Yes, I will solve all the gate questions in this lecture. Okay. Now I'm telling you that set of all rational numbers are countable. So how to show it? Very easy. If you have any number and you know, just apply the countability lemma. Just remember the countability lemma you need to apply. And what I will do, if you have any natural number, any rational number p by a by b, then what you do, you assign this a by b to mod a plus mod b. This is what you do. For example, what you do, if you have, let's assume you have 1 by 2, so you assign this 1 by 2 to 3, means 1 plus 2. If you have minus 1 by 2, then you assign it to minus 1 plus 2, basically 3. The basic point is that if you have a by b, then you assign this a by b to this modulus a plus modulus b, basically making it positive. Okay, if you have, for example, if you have minus 2 by 3, then where will you assign it? You will assign it to modulus of minus 2 plus 3, that is basically 5. So you will assign this to 5. Now let's see whether this assignment is satisfying all the conditions that we want or not. This assignment, basically I have a by b, then what I am doing, I am assigning this a by b to mod a plus mod b. Now if I do this, then definitely this, I told you, every element here, this is set of rational number. Every element, for every element you must have unique natural number. This is true, because if you have any number, like if you have 1 by 2, then this 1 by 2 will be assigned to 3. So you can see that for every rational number you have a unique uh, unique rational number, unique natural number here, except 0. If you have 0, okay, 0 is very easy to cover, because just assign this 0 to 1. Don't worry about this 0, okay, because what you can do, you can assign this 0 to 1. Now what I'm doing, for every rational number can be assigned to unique natural number. Now also the second condition says that to every natural number you must have finite number of elements that are assigned to it. So you can see this is also true, because consider any natural number, whatever natural number you want to consider. If you have, for example, natural number 4, then to this 4 how many numbers you have assigned? To this 4 you have assigned, for example, one you have assigned, you can say 1 by 3 you have assigned, okay, like, okay, 2 by 2 you have assigned, or you can say 3 by 1 you have assigned. These numbers you have assigned to 4. Also negative, minus 1 by 3, minus 2 by 2, and minus 3 by 1. So you can see that if you have this natural number, to this natural number how many numbers you have assigned? only a finite number of elements. You can do this for any natural number, whatever natural number you have. For example, if you have 100, then to this 100, how many numbers you have assigned? You can find it very easily. You can find it, okay, because you know to this 100 I have assigned those numbers for which this is doing this is, and you can see this equation has finite number of solutions. Okay, this you can find how many solutions are there, this you can find. But the point is that to every natural number I have assigned only a finite number of elements. Hence the countability lemma says that, from the countability lemma you can see that set of rational number is countable. Anyone has any doubt in this, let me know. This countability lemma is, remember, very important. Very easily you can solve if you once you practice it enough. Once you practice 10 or 20 questions, this countability lemma will solve all your problems. Now let like I will show you when we will take this gate exam questions. So let me first take gate exam questions so that it will give you more motivation. Okay, we will come back to other things later. Let me solve these gate exam questions. This is gate 2018 question. He is saying set n be the set of natural numbers. Now some set are given to you and he is asking which of them are countable. So this is the question. Now let's see this first P. P is saying how to say we got finite set in rational number example. In the rational number example 9, if you see that to any natural number, for example, if you have this natural number 3, then to this 3, what are the elements you have assigned? To this 3 you have assigned like this. For example, this 1 by 2 you have assigned to 3. This minus 1 by 2 you have assigned to 3. For example, this 2 by 1 you have assigned to 3. Minus 2 by 1 you have assigned to 3. So you can see that this number, you can see this, these are the numbers that you have assigned to 3. So to this natural number you have some finite number of elements. Okay, to any natural number, to 4 you have some finite number of elements, to 5 you have some finite number of elements. Actually for any natural number you can find using combinatorics. If you remember your combinatorics, then from that you can very easily see that this is the equation, number of non-integer solutions, something like this, number of non-negative integer solutions. So this is a, you can say, part of combinatorics, if you remember. So in combinatorics we study this type of problem, number of non-negative integer solutions. Like if I say that a plus b equal to 100, then how many solutions are there for a comma b? There are finite number of solutions. Okay, and how many exactly, that also you can find. Actually there is this if you remember, a plus b is equal to 100. So how many number of solutions will be there? That will be basically 100 plus 2 minus 1 c2, I think, like this. So there is this formula, n plus r minus 1 cr. So you can apply that formula actually. So this is from combinatorics. You can just go to the combinatorics, and today you can study about number of non-negative integer solutions, or you can find number of positive integer solutions. So very easily you can do this actually. But my point is not to find what is this solution. My point is only to find that to every natural number I have assigned only finite number of elements. My target is that. Once my target is fulfilled, okay, I don't care how many elements. I don't care about how many elements. I only care about that there should be finite number of elements. This is my concern. Okay, are you getting this point? So to different, for example, to this one only to this one, no one is assigned to this one. To this one you can assign 0. Okay, maybe you can assign 0. Now to this 2, 1 by 1 and minus 1 by 1, these are assigned. So you can see two different natural numbers, you can have different number of elements assigned. But the point is that to this 2 you have finite number of elements, to this 3 you have finite number of elements. To every natural number you have finite number of elements assigned. So that is the concern actually. Now let's see this gate question, gate 2018 question. Okay, and let's very easily you can do this. This is your set of rational numbers, positive and negative. This we have already seen. This is countable. The proof also we have seen using our countability lemma. Okay, Very easily you can see. Now let's see this q. He's saying set of functions from 0 1 to n. So let's see q. He's saying set of functions from 0 1 to n. So how to let's see whether this is this set of functions is countable or not. Okay, let's see this. How can we do it? Very easily you can do it actually. First of all, you need to see what is this q. This q is basically some functions, f1, f2, f3. Some functions are there because this q is basically set of functions. So in this you have every element is a function. Now this every element is a function from 0 1 to n. So you have 0 1 and you have this n. So from this 0 1 to n you have function. Of course, if any function you define from 0 1 to n, that will look something like this, either like this, or maybe this 0 can go to 2, 1 can go to 4, so like this. So you can see, for example, this f could be like this f1 may be like this 0 is going to 0 and maybe this 1 is going to 2. So this is your f1. This f2 could be like this, 0 is going to 1 and maybe 1 is also going to 1. This f3 is also a function. So you can see every function, if you see in this queue, what you have functions. So every function is basically like this. 0 is going to a and 1 is going to b. This 0 is going to some element a and 1 is going to some element b. You need to understand what is this queue. I am just okay right now, I am just telling you what is this queue. This queue is a set of functions. So in this queue you have functions f1, f2, f3, f4. These are the functions. So these functions are the elements of queue. Now this f1 is a function from 0 1 to this. So for example, this could be f1, for example this could be f2. From this you can understand that every function will look like this. Every function will look something like this. This 0 will go to a and this 1 will go to b, where this a and b, these are natural numbers. These are natural numbers. So these are this is your queue. So far I have just told you what is this queue. Now we need to show that this queue is countable. So in this queue, what you have, in this queue you have like this. This is an element of queue. 0 is going to a and 1 is going to b, and some like this. Now what I will do, again I will apply the countability lemma. I told you, very easy, countability lemma. So in countability lemma, what I will do, I will map this element to a plus b. Very simple. Okay, I will map this element to a comma b. That's very simple. Now you can see that every element is assigned to unique, because for example if I have 0 comma 0 0 comma 1, then this will be assigned to 1. For example, if I have a function which is like this 0 comma 2 1 comma 2, then this will be assigned to 4. So you can see every element is assigned to unique element. And what is that unique element? That is a plus b. So this is okay, this is okay, this is done. On other side, what I can say, that to every number you have assigned finite number of elements. Because for example, if you have 4, to 4, what are the elements you can assign to this 4? To this 4 you can assign those elements. For example, to this 4, what you can assign? You can assign those elements where a plus b is equal to 4. So you just need to find the number of non-negative integer solution of this equation. What is the number of non-negative integer solution of this equation? That is equal to basically 4 plus 2 minus 1c 2, n plus r minus 1cr. Again, this non-negative integer solutions you can find. So you can see that if you have any natural number, then to that natural number you have only assigned some finite number of elements. Are you getting this point? So you can see using countability lemma how easily you can prove it. Very easily you can prove it that this is countable. Anyone has any doubt in this? This countability lemma is actually very easy principle, and if anyone understands this principle, or if you practice it enough, if you solve, let's assume you solve 10 questions on this countability lemma, then I guarantee that you will be able to solve any countability question. Every countability question you can very easily solve if you know this, if you practice this countability lemma very you can say enough. Just practice. I have taken many examples so far, and I hope that you can solve. You have understood this countability lemma. If anyone has any doubt, then you can let me know. Now these are set of functions from n to 0 comma 1. This is actually uncountable. Why this is uncountable, that we will see in the next lecture. So in this lecture we are focusing on countability. Okay, like all the questions that I will take, in all those questions I will apply countability lemma, and using countability lemma I will show that this whether that set is countable or not. In option A, more than one element is mapped to single element in set N. So yes, Siddhant, actually you are okay. You are putting a very nice point, but actually what you can do, see, Siddhant is putting a very nice point. Siddhant is saying that, for example, in the set of rational number, when we were putting this set of natural number with set of natural number, in that case, if you see what I did like this: A by B. I mapped this A by B to A plus B. This is what I did, if you remember. But if you do like this, then what will happen? This 1 by 1 will go to 2, and this 2 by 2 will go to 4. But actually 1 by 1 and 2 by 2 are same. This is Siddhant, this is your doubt, right? So you can see 1 by 1 is going to 2 and 2 by 2 is going to 4. But actually 1 by 1 and 2 by 2 both are same. Both are actually exactly same. So now you can think, okay, that actually the first property is not satisfied. The first property says that for every element here you must have unique element here, that you must have. So actually that property is satisfied. Let me tell you why. Because consider the situation, okay, that property is actually not that much strict. Why? Let me tell you. Assume that you have element A, and let's assume that this element A is going to natural number 1 also, and this element A is going to natural number 2 also. Now I told you that to this natural number 1 there should be finite number of elements. So let's assume with A there is B, there is C. I told you, because for every natural number you must have finite number of elements. Now with this natural number 2 also you must have finite number of elements. For example, maybe P comma Q. Now at this point of time, what you can do, you can just remove this A from here. What I will do, I will just remove this A from here, from this set, that is it's like this A is already assigned to 1. So if this A is assigned to any other element, let's assume if this A is assigned to any other element, I can just remove it. I can just remove it, remove it. If I do like this, then you can see one thing, that this A will be assigned to only one element. And remember, because to this 2 only finite number of elements were assigned, if I remove one element, then still that is finite number of elements. So are you getting the point? The point is this: if somehow, let's assume I defined a rule, and let's assume if due to my rule some element is being mapped to more than one elements, due to my rule it is happening that this A is getting mapped to more than one elements, then what I will do, I will remove this A from these from here, and this A only I will assign to 1. Now if I do this, then remember, if I do this, then still to every natural number only finite number of elements are assigned to that natural number. Okay, so that is why actually this first condition is not that much strict. Like you don't have to worry about this first condition. So far I have been telling you this is set A, this is set of natural number n. What I told you, that for every number here you must have number here. So actually you don't have to worry whether this number is being allocated to unique element or not, because if it is allocated to unique element, then that is very fine, that is very nice. But if it is allocated to more than one element, then you can always remove it. So actually the very important condition is this second condition, that for every natural number you must have finite number of elements. So this is the most important condition. For every natural number, if you have a natural number x, then for this natural number x you must have finite number of elements. This is the most important condition. If you can do like this, and remember every element of A must be covered, like for every element of A at least one element must be there, so every element of A must be covered. If you can do this, then we will say that A is countable. So this is basically your countability lemma. This countability lemma is very useful. You will see many examples we have already seen so far. Now let's see this example. Set of finite subsets of n. Okay, let's see. Now you tell me how to apply this countability lemma. Basically, you have a set of finite subsets of n. Set of finite subsets of n. Okay, so first of all, just understand what is this. In this set R, you have set of finite subsets. So basically all elements are finite subset. For example, 1 comma 2 is there, for example 5 is also there, for example 1 comma 2 comma 3 is there, 3 comma 4 is there, and so on. Set of finite subsets of n. So in this set R you have these elements. Now we need to show, okay, let's see whether this R is countable or not. So can anyone apply countability lemma? Using countability lemma, can anyone give me proof what I should do? Like if I have this element, let's assume I have this element A comma B comma C comma D, then to which element, to which natural number I should assign it? This is your set R. In this set R, every element is a finite subset of natural number. Remember, every element is a finite subset of n. So you can see in this R you have these type of element like this, or maybe for example maybe 2 comma 3, or maybe for example 1 comma 2 comma 3, like this. So can anyone give me how to apply countability lemma? Like to which element should I assign it? Yes, right. Yes, Siddhant is correct. So what I will do, very easily, I don't have to worry about it actually. What I will do, I will just assign it to 2 plus 3. I will just assign it to 1 plus 2 plus 3. I will just assign it to A plus B plus C plus D. So basically what I am doing, every element is covering, because for every element I have some element here. For example, okay, don't have to worry about these small things, like okay, where to map this empty set. Just map it to 1. Okay, don't worry about it. Why? Because you know that to this 1, whatever you are mapping, if you include one more element, that does not harm you. Okay, you have a finite elements, set of finite elements. If you include one more element, there is no problem. So you don't have to worry about these corner cases. This is a corner case, you don't have to worry about. Okay, you can always accommodate this corner case. Remember the Hilbert, this Hilbert Grand Hotel. Hilbert Grand Hotel says that you can always accommodate new person. So remember that. That's why you can always accommodate one element, always. So you don't have to worry about this corner element. Now you can see every element can be mapped to like this. Now if you do like this, then you can see that every element is getting mapped to some natural number. Now the main important thing is, to every natural number how many elements you are assigning. That is the important point. To every natural number, if I have for example, if I have a natural number 4, to this 4 how many elements I am assigning? Can anyone tell me? Can I guarantee that only finite number of elements are there? Can I guarantee that? Only finite number of elements are there. Can I guarantee? So actually you can see I can guarantee it, because to this 4 what are the elements I will assign? To this 4 whatever element I assign, whatever subset I assign, that subset cannot contain any element greater than 5. You just need to focus here. To this element 4, how many elements I will assign? Whichever element I assign, whichever subset I assign, that subset cannot have any value greater than or equal to 5. Any value greater than equal to 5 cannot be there. Okay, this is enough. This is enough to, I don't care about exact number. I don't care about exact number. My only point is that are there finite number of elements or not? Yes, there are finite number of elements, because in all these elements, the no number greater than or equal to 5 will be there. Okay, and only these numbers 1 2 3 4, only these numbers can be present, and using these numbers only a finite number of subsets you can make. So you can see that to this element 4, only a finite number of elements are assigned. You can take any natural number. If you take any natural number x, and to that natural number x, how many elements I am assigning? To that natural number x, whatever element I am assigning, in that element I cannot have any value greater than or equal to x plus 1. Okay, I cannot have any value greater than or equal to x plus 1. So this is enough for me to say that to every natural number I have finite number of elements. So this is how you can very easily prove it. Now actually let me tell you one thing. Many students are there here who could have answered it. Actually this is very easy to answer this question. Many students can answer it. Okay, they can directly say that okay, these are the countable set. But understanding this is important. Answering is not that much important. Understanding is important. Now you can understand that all these PQRS, we have proven them. PQS, and this R we will see tomorrow. Okay, so next question, this is also gate question. Consider this. So let me tell you few things about from TOC. Let me give you some results from TOC. Okay, so actually the time is almost over. So the remaining things we will see tomorrow, and tomorrow this countability and uncountability both will be over. Tomorrow what are the topics that we will take? Let me tell you. We will take Cantor's diagonalization theorem. Okay, so this is a very important actually concept, Cantor's diagonalization concept, and this we will use to prove uncountability, that there are different levels of uncountability. This we can very easily prove using Cantor's diagonalization theorem. So this is a very important topic that we will see tomorrow. Also we will see all the remaining gate questions. Okay, because the concept part is over. Every concept that I wanted to cover I have already covered. Now only the questions will be remaining. The only one concept that is remaining is Cantor's diagonalization theorem, and this also we will prove it. This also we will study using examples. So we will take almost 5 or 6 examples, and for those set we will prove that they are uncountable. Okay, so this is the things that we will cover tomorrow.